Hi there. I wanted to talk about a toroidal plasma globe today that I made. It uses a self-resonant Class E oscillator, and it runs at about 14.5 megahertz. You can see it here. I've just started it up, and it's generating a stable ring of ionized xenon in the 2-liter glass ball that is filled with xenon and oxygen. Here's the driver circuit down here. It uses a ceramic doorknob cap as the RF capacitor, and the primary winding is 2 turns of 6 millimeter copper tube. And if you want to call it a secondary, the secondary is a single shorted turn of ionized xenon inside the plasma globe. Right now it's being supplied about 36 watts from this benchtop switching power supply. The power supply is in current limiting mode. I've found that to be more reliable and less likely to destroy the FETs on this board. However, I've seen a lot of people get it to work with just a normal voltage mode switching power supply, like a wall wart or a laptop power brick, for example. On the scope here, you can see the drain waveform in blue and the gate waveform in pink. The gate waveform is AC coupled, and I've tried to show it at about the right amplitude on the scope display there. As you can see, there's actually not that much gate amplitude. The gate of the FET is not being driven that hard. This seems to work all right, although you could probably get slightly higher efficiency by driving the gate even harder. I really haven't seen that to be necessary. And the only thing that really gets hot on my driver is the glass itself. And I think that makes sense, considering there's probably 25 or 30 watts of heat being put into the ionized xenon ring that's in there. The other thing that gets slightly warm is the RF cap, the RF transmitting doorknob cap. And I guess that's probably just due to dielectric loss in the cap. The board itself uses 2 parallel Gen 3 Optimos Infineon FETs. And they're like 250 volt rated parts that have something like 100 or 200 milliohms of on resistance. Have yet to see them really produce much appreciable heat. There is a tiny little compressible thermal pad between the bottom of the board and the heatsink below it. The heatsink is oversized, really just to act as a base for the lamp to sit on. And the arms that hold up this coil are just made out of chrome-plated steel wire that I soldered ring terminals onto, and then bolted through the board into holes in the heatsink. The primary is attached to the support arms just by zip ties, and the support arms are insulated with heat shrink. The primary turns are just spaced apart by some, it's like PEX or polyethylene tubing that I just cut into little pieces and then slit. And the distance between the plasma globe and the copper winding is set just by adding or removing these little slitted spacers. Here's the basic circuit. You can see the power supply driving it is shown as a current source here with a 20 volt compliance range. There is a 200 nanofarad capacitor immediately on the input just to make sure no RF ripple gets back to the power supply. The radio frequency choke here isn't very critical, but it's just an air core. Here, I'll show it to you on the physical board. There's the RFC. It's just 18 gauge wire wound around about a 25 millimeter PVC form and soldered to the board. There's a capacitor on the drain, which is 470 picofarads. There's 2 of these FETs and 2 gate drive resistors on the actual circuit, but I only drew 1 here in my schematic for clarity. The 1.3 microhenry inductor here is the copper primary that I was showing you earlier. The RF node, this is the node that generates a high voltage or develops a high voltage across it. It's actually the bottom turn of this coil, and there's Litz wire that connects that bottom turn to the RF cap down there. I wanted to put this high voltage and high frequency turn on the bottom to avoid like excessive electric field coupling getting into the globe and potentially disrupting the orb. You mainly want the energy that's transferred into the globe to come from magnetic field coupling rather than electric field coupling. And as I'll show you in a second, if you have too much electric field coupling into the globe, it doesn't like to hover in a neat little ring. Instead, one end of the ring will tend to get stuck down near the primary winding. And you can reduce that effect by putting the high voltage, high frequency turn on the bottom, as well as adding space with these little slitted spacers between the glass globe and the primary winding. Okay, back to the circuit here. There's a gate capacitor here, which just forms a divider with the RF cap to get the gate voltage reasonable. The gate drive resistor, it may not be entirely necessary depending on what kind of FET you get and how slow the FET is. I'm using pretty fast modern FETs here, so I did need a gate drive resistor in order to get an adequate amount of phase shift between the capacitor divider node here that I'm pointing to and the actual gate of the FET, in order to achieve this waveform here that you see on the screen. And as you can see, there's a good amount of phase difference between the drain waveform rising up and the gate waveform swinging positive, such that the gate of the FET is turned on. It actually looks like the timing is slightly off here, and I think that's okay because the FET does have an internal turn-on delay time. And so by the time you account for that internal turn-on delay time and the phase of the gate signal here that I'm probing, I think you find that the FET turns on at just about the valley of the drain voltage waveform here. And I think, as evidenced by the fact that the power dissipation in the driver is really low, I think I've achieved pretty good timing here. I'll go back to the circuit just briefly so you can get a full view of it. The gate is biased up. The gates of these FETs here are biased up to about 4 volts. And I do that. I've just built a current source with 2 PNP transistors, which I've just run as a current source here. And it just steals 1.5 milliamps of power from VN and pushes it down through a potentiometer, which is the 10K potentiometer here. I didn't write that, sorry. And then this is an 8.2 volt Xenon diode that forms an 8.2 volt reference. So you want to just keep the potentiometer right about in the middle of its range, which is about 4 volts. There's just a cap to make sure that no RF gets back into this current source. And then a 10K resistor, really just to drive DC to the gate. And 10K is a pretty high impedance, so not much RF can get shorted back into the voltage output there. So this circuit starts up pretty reliably and runs. As you can see, it produces a nice stable hovering plasma toroid. So I do want to show you something, which is what it looks like when you perturb this thing and get the ring to actually oscillate. And so one way to get the ring to start to move around is just to increase the current, put a little bit too much power into the globe. And then at that point, it becomes easy. You see, as I increase the current, which I'm doing right now, the ring kind of gets more and more unstable, and it kind of gets dragged down towards the primary. And I think that's just due to the magnetic and electric fields getting stronger as I increase the current. And then you end up at this point where the ring really is strongly wanting to interact with the primary coil. And I think that's because the field is so strong that there's always one side of the shorted turn in the ring of plasma that wants to get really hot. And so it sits right near its side on the primary and gets really hot, and then convection causes it to rise up, and then the other side takes its turn, and so on. And so you end up with this ring of plasma kind of dancing around. And that's certainly an interesting effect. You can also see that on the scope, in that the drain and gate waveforms dance around a lot. Again, I'm driving the gate really weakly here in this configuration. You can reduce the gate capacitance there, that 8.8 nanofarad cap. Can reduce that to drive the gate harder, but I haven't really seen that to be necessary. And the transistors are really not getting warm at all. So I really don't see any reason to do that. It seems to be pretty safe to operate here. One other thing to note is that the way I'm changing the gate and drain capacitors is I just have 0.1 inch headers that are shorted with jumpers, just shorting jumpers. And so I just have like the maximum amount of caps populated on the board that I think I might need. And then I can just add and remove caps just by shorting or unshorting the corresponding pins on the 0.1 inch header here. So I found that to be a really easy way to tune this circuit. And to probe the circuit, I found it really difficult to use actual scope probes. And so I just built a low impedance probe into the board, which presents 50 ohms to the end of the cable that screws onto the board. And then on the scope itself, I use 50 ohm terminators right as the signal goes into the scope. Due to the really strong E field and common mode noise at 14.5 megahertz that the driver and globe generates, I found it to be really necessary to stick ferrite beads. These are just clamp-on ferrite suppression beads on all the cables. And that's just to provide common mode rejection, so I can get signals in and out of this thing without forcing a bunch of common mode current into the scope, which will throw off the readings. The other thing is it's really important to get a good ground, and my ground probably isn't good enough. I'm just grounding it to this triple output power supply, but it's probably better to actually like find a water pipe or something, right? A copper water pipe, or use a ground rod or something of that sort. This is actually like a piece of power ferrite, this toroid, and I had fewer turns on it before and found it to get kind of warm, which is really kind of interesting. It suggests that there's actually a lot of RF that wants to creep back through the cable to the power supply. The power supply has its negative terminal and its ground shorted together, which is really just a safety measure. It really shouldn't be necessary if you get good enough common mode rejection on the cables. I can't really think of anything else to say about this, so there it is. There's the completed plasma toroid and the scope waveform and the circuit that I built. Thanks for watching, and please give me a thumbs up if you enjoyed the video.